Greetings and welcome to this presentation on threats to validity and also just a smattering of miscellaneous topics in the research realm. My main objective for this is to build upon what I presented in the last screencast, and a lot of the things from that screencast and this one go hand in hand, and maybe it would have made more sense to make them into one, but I think that it can get a little overwhelming if too much is presented at once. So what I want to do is do a bit of review and then head into some more complex thinking about research, and know that you will get an even more thorough treatment of these matters coming up in program eval. Okay, so let's review the 4 quadrants again. Recall that we have 2 ways we can be wrong. We have the type 2 error and the type 1. And the definition of type 1 is the probability that we will fail to detect an effect in our study that really exists in the population. Please memorize that. Know that it always starts with the probability. That is a reminder to us that everything in stats is couched in terms of likelihood. Conversely, type 1 error is the probability that we will see an effect in our study, we'll observe some kind of relationship, and in reality, that effect does not exist in the population of interest. So what I failed to talk about in the last screencast is, are there some ways we can know which quadrant we inhabit, especially when it comes to these errors? So are there some warning signs that we can look for that we could say, ooh, we are probably committing a type 2 versus a type 1? And this will be very helpful for you when you get into practice, into research, whatever your career goals are, because when you do not detect an effect that you expected to see, your clients will want to know, if this effect does exist, why couldn't we see it? And you will have some reasonable explanations and some things to try in the future to increase the likelihood of detecting that effect. Remember, these are the validity definitions. Please memorize them, know the distinctions among them, and I'm going to point a couple salient ones out here. The first 2, stack inclusion and internal validity, are related, but they are distinct. Statistical conclusion validity has to do with statistical association only, not causation. So we want to know if it is accurate to conclude that these 2 variables are statistically related to each other or not, if we don't find an effect in our study. Is that a truthful inference? For internal validity, it's more about causation. In fact, it's all about causation, I should say. So we want to know if the proposed IV caused or moved the dial on the DV. So we can have statistical conclusion validity without internal validity, because we can all think of situations where there is a correlation but not causation. However, if there's causation, the two variables will always be statistically linked, or should be, if we have enough power to detect the effect. If we have reliable measures, etc., we can't have internal validity without statistical conclusion validity, but we can have stack conclusion without internal. Construct validity, remember, is the strength of the correspondence between the theoretical essence of the construct we're trying to capture and the operationalization we're using to capture. So for example, just this came to mind when we're talking about measuring people's moods. We can either ask them outright and subject ourselves to any biases that people may have in wanting to make themselves look like they're in a better mood than they are, or a worse mood than they are, as it were. So, you know, people have intention maybe or opportunity to distort when we simply ask them. Or we could use a computer to scan their faces to detect people's moods based on their facial features. And those are probably more difficult to distort, some would argue. Although you can probably find a fault with both ways, actually, of operationalizing. But the point is that when you're thinking about a construct and capturing it, what is the method, what is the operationalization that will best capture that essence? And that's not an easy question, as Aronson reminds us. Finally, external validity, and that's the truthfulness of inferences that there's a cause-effect relationship, and does it extend across different kinds of participants, people in our study, different settings, different cultures, different ways of measuring or manipulating our variables, and this gets into the construct validity realm as well, so these two can overlap somewhat, and that's normal. Sometimes it's not easy to make a clear distinction, is this construct validity versus external, because again, the two ways to measure mood, as I just talked about, sometimes we may see the effect better when we use the computer analyzing the facial features versus just simply asking. And these are all things that we as scientists have to think about and make a logical case for why we chose to capture a construct in the way that we did, and does it map on conceptually like we would like. So let's start with stack conclusion validity. Usually when we do not find an effect that we are pretty sure is going on in reality, that's when we're going to be looking at stack conclusion validity issues that are listed here. In other words, when we commit a type 2 error, or we think we have. And type 1 is usually the error that everyone wants to avoid. We don't want to falsely claim that something is working when it doesn't. And that's how the publishing industry works. We just can't have type 1 error, so we make our p-values very small, like 0.05 or 0.01. But I want to challenge us to think about type 2 error and the cost to committing that instead. So if we want to show that there is prejudice or bias operating, for example, or we're selecting people based on a wrong factor such as prejudice or bias, we want to show that, and when we commit a type 2 error, we aren't demonstrating that, and then we can't work on the problem. And so there's a person in our field named Herman Guinness who talks a lot about how the cost of type 2 error in our field, and how we may have been negligent in not finding things because we're not properly powered, we don't have enough people in our sample. Of course, null findings aren't published, and a lot of those null findings may have been significant if they had had more people, better measures, different things had been controlled for, etc. So it's not like type 1 or type 2 error. It's not like type 1 error is not always the worst kind of error, but that's how we functionally work in science. And I guess I just want us to think that presupposition through a little more carefully and realize that type 2 error may be a worse error to commit than type 1 in some situations. So the point is to think through the costs of committing both kinds. And then if you feel like type 2 is the more costly error, not finding something that's really there, because people could potentially be hurt if we don't find this effect, then consider raising that p-value to 0.1 or even 0.2. And that's what Herman Guinness talks about. Okay, little side dish there. Moving on. Okay, so we are more likely to miss an effect that is really present when we don't have enough n size. So if we don't have enough people in our study, we are less likely to find significance. So that's what it means to be underpowered. And I guess I should do some editing here. Let's just say effect size in the I'm just going to edit on the fly here. If the effect size in the population is small, then we're more likely to commit this error, especially if we don't have enough n. So let's say that there's just a little bit of prejudice happening, that people have unconscious biases that aren't affecting their decisions too much. So the DV is not moving a lot with this bias, but it's moving a little bit. And you as the researcher understand that even a little bit of bias over time can really cause some damage to your company, let's just say, in the hypothetical. And so you would want to pick that up and be able to start working on it, even if it is a small effect. However, the smaller the effect is in the population, the more likely that it's going to be very hard to find. And so that's the trade-off that we have. If there's a big effect in the population, then you won't need as much N size to find it. But if it's small, then you'll need a lot of N, and you will need really precise measures to pick it up. Also, range restriction on either the IV or the DV can cause you to miss an effect that's really there. So if everyone is responding 6 on a scale of 1 to 6 or 1 to 7, because they just want to respond positively, I don't know, then you're going to have trouble seeing a correlation. So I say something that's kind of funny. I've said it for many years now, so I'm going to repeat it here because I'm not afraid to sacrifice my dignity on the altar of education. But if you ain't got variance, you ain't got covariance. And that just simply means that two variables cannot be correlated if one or more of them doesn't have a lot of variability. So if you have all women in your study, for example, or mostly women. So let's say your proportion is 10% female and 90% male, or vice versa. That's not a lot of variability on gender, so you're not going to find effects, significant differences between men and women on any stat test basically that you run. And that's because we don't have variability on gender. We don't have an equal number of men and women, or approximately so, in our study. And so we're not going to find any differences, or gender's not going to correlate with anything. So when you don't find results that you were expecting to see, look at your standard deviation, your variance on all your variables, and see if some of them didn't have any variance, then that could be why you're not seeing the effect. If you violate assumptions of your stats tests, then sometimes this will cause type 2 error as well. Sometimes it will cause type 1, but in my experience, it usually goes to type 2. Too much within group variability on the DV of interest. In this, I should show you an example in class of this, but basically what happens when you have an intervention, people in an intervention and who aren't in an intervention. And when there's a lot of variability on the DV in the intervention group and a lot of variability on the DV in the non-intervention group, then it's more difficult to detect differences between those two groups, because that within group variability creates too much noise, and you really can't see the effect as easily. So this may feel like a contradiction from what I said earlier: if you ain't got variance, you ain't got covariance. Well, there's a difference. You want maximum difference between groups, in between group variability. So the means on the groups should be very spread apart to find an effect. That's the effect size, basically. The difference between the mean of the people who are in the intervention and the people who are not in the intervention. That mean difference is wide. If it is wide, then you know that you have an easier time finding an effect. But if that difference is smaller, then you would have a harder time finding an effect. And the within group variability creates more error, because with any test, whether it be a F test or a T test, basically what you have is a ratio, and that ratio is between group variance over within group variance. And with that ratio, you want a big numerator and a small denominator in order to have a large T or a large F test, and thus more likelihood of significance. So to the extent that you can reduce within group variability and increase between group variability, then you have a strong test. But if you have lots of within group variability, it's going to be harder to find an effect. Now, the way that we can fix this to some degree is to have a very strong manipulation. So there's no ambiguity in your IV. Your IV is producing the intended response in your participants that's going to move them way far from the control group. That's the idea. Or if you have a program in an organization that you're attempting to evaluate, that program is going to be a very strong program, meaning that all of the people who take the program are going to be highly affected, such that they're going to be pretty homogeneous in how they respond to the DV. versus the people who weren't in the program. And good programs do that. Good programs increase the people's skills who are in that program, and they increase them all together. Of course, there will be some within group variability. It's inevitable, but the goal is to reduce it. So in class, try to remind me, and I will draw an illustration that hopefully will be helpful for this concept. Finally, unreliable measures that don't consistently reflect a person's true standing on the construct of interest. So imagine that you have raters who are rating target people's behaviors like participants. Maybe you have some raters judging a child's aggressiveness in the lab. So you have an intervention for the children, and then you have raters who are blind to your hypotheses and blind to condition and are rating. Maybe the raters get tired and they start to make more errors, and that is going to impact the reliability of the measures such that it'll be harder to see an effect if those raters aren't consistent with one another and consistent with how they're rating each child. So that is going to be important. And then also the two raters rating the same target need to agree with each other to some extent and be consistent with that target's behavior. And to the extent that they're not trained well and they're not doing that, then you're going to see less of an effect. Okay, moving on to internal validity. Internal is the truthfulness of inferences of a causal relationship. I believe that internal validity is super important to think about. As I talked about in the last screencast, causality is something that we're never done exploring. I heard somebody talk about, and I've done a little bit research in the diet realm and like certain foods, what's best for the human body. And it's very interesting because there's this whole notion that cholesterol produces heart disease. And people have assumed that, in fact, many, even scientists, dietary scientists, have assumed this causal relationship between the two. Well, what if, here's what some people are saying, what if heart disease is really caused by inflammation inside your blood vessels? So what happens is stress, some would say, and sugar, too much sugar, but mainly stress, and some would even talk about the different oils that we eat that are not natural. Now, olive oil is good, but canola oil has been invented just in the last, 40 years or so. So the human body has not had it for an extended length of time, whereas people have been eating red meat for many, many thousands of years at this point. And so those oils, some have been saying, and there's some scientific evidence that these oils are causing inflammation in the blood vessels, and that inflammation causes the blood vessels to be thinned, and the body produces cholesterol. The body produces it, and it gets it from the food we eat as well, like the fats such as what's in bacon and dairy and red meat and things like that. And it lays down this cholesterol basically to save your life. So your blood vessels are thinning from stress and things are eating away at them, and the body puts down the cholesterol to save your life so that your vessels don't basically burst and cause death. So do we really want to stop that process? Is it good to infer that cholesterol, if it is indeed saving you from death because of inflammation inside the vessels, is it right to conclude there's a causal relationship between cholesterol and heart disease? Or is it the inflammation that's causing the heart disease? Mainly the stress and the things we've been eating in our diet that are not the best, like those oils, etc. And so what's really causing what here? And so someone has said, it was very interesting, they said blaming cholesterol for heart disease is like blaming the firemen for starting the fire. So the firemen are there actually to put out the fire and to save our lives, but and so that they were likening that to cholesterol. So is cholesterol really the enemy is the point? And so this really, and I know this may sound radical to some of you, but I get to thinking about it sometimes because the recommendations that we make for the welfare of people and the decisions that we make, pardon me, the decisions that we make are based on our theories of causality. And just because things are correlated doesn't mean there's causation there. And I thought that was a good example of just something to think about, if nothing else, that are we giving people the right advice based on our theories of causality, and are we really doing the proper research to be able to disentangle those effects? That's why internal validity matters, in other words. Okay, so we can have reverse or reciprocal causation, so ambiguous temporal precedence. We can believe that an IV is causing a DV when really it's the other way around. And I think the biggest example of this in our field is job satisfaction and job performance. Many people think that it goes, the causal flow goes from satisfaction to performance, when in reality it may be that when we are performing well on our job, then we will be more satisfied. Or it's reciprocal. They feed off each other in a cycle. So some things to think about there. And we have other things that affect internal validity as well. And usually internal validity threats make us cause us to commit, I should say, a type 1 error. Usually not type 2, although I can probably think of exceptions, but usually it's a type 1 where we're falsely concluding that there is a causal relationship when there isn't one. So things like maturation, if we give people a pretest and then an intervention, a post-test, especially if it's over like some months or years, people naturally are maturing and learning and growing, and it could be that they ended up at the same place on the DV at time 2 without the intervention. So they just matured on their own. We would need a control group to ascertain whether maturation is working. Testing effects. So sometimes when we do a pretest, we are getting a baseline of someone's feelings or attitudes, and then we give them an intervention and then a post-test. But the pretest gets them thinking. It primes them to think about their attitudes, maybe prejudice or biases, and then they do some work on their own, and then on the DV they score better, but not because of the intervention necessarily, but just because we've primed them with the pretest. History effects are things that impact us that are not the intervention, but that will cause a change from time 1 to time 2 on the DV. So if you give a pretest and then an intervention and post-test, and people hear something on the news that impacts them and their performance drops, or something happens in the company and performance drops, then we'll conclude our intervention didn't work, when in reality it was the event that happened that kind of messed up the plan. This can work for either a type 1 error or type 2 error, depending on the event. We'll talk more about that in Program Eval. And finally, selection. This is our basic confound, like I discussed in the last screencast, where people who volunteer for a program or an intervention systematically differ from people who don't. And so when we test them at the end, that we will see differences, but it's not due to the intervention, but it's due to those systematic differences. For example, people who enter an interpersonal skills training program are more likely to have higher skills and propensity for having propensity to be highly skilled with interpersonal relationships from the beginning. So there are ways to rule these out with design controls, and we'll talk more about that later. It's beyond the scope of this a little bit. I'll touch on it a little bit further in a future slide here, but okay, construct validity. Construct validity is really important, and again, I have another example of it's kind of conventional wisdom about diet. Every so often I see a study come out that says red meat's going to kill you. Well, that makes me wonder, because people, again, have been eating red meat for thousands of years. The Native Americans ate buffalo for many thousands of years, and they didn't have nearly the health problems, in fact, that we have today. They had their own health problems, no doubt, but they didn't have the chronic disease that we see now. So that gets me thinking, is it really red meat that's the issue, or is this a construct matter that people are assuming red meat is one thing when it's really another? And let me explain that. Eating red meat from animals who have not been under stress, so animals who have peacefully lived on pastures have had the grasslands, fields to roam, forests, wherever, and as nature has intended, basically. So we can eat meat in two ways, I think. We can eat meat the standard American way that's highly processed. Animals have been stressed, kept in very confined spaces, and fed horribly crazy food like antibiotics and chicken poop, etc., and all manner of other things which we won't talk about. Or people can eat meat that has been not been tampered with, in the sense of it's the way nature has intended, where the animals aren't stressed, they're living in peaceful areas, and they are not fed anything but what nature intended. For example, cows are meant to eat grass and hay, not corn and grain, for a long period of time. I'm sure they can have it for a little while, but if they have it their entire lives, it makes them sick. And so what you're eating is a sick animal if you eat a grain-fed cow. And so grass-fed cows are much different in their nutrient profile than grain-fed cows, if you do the analyses on their nutrient profiles and what vitamins, etc. And incidentally, much more healthy for the body, people are finding. So when these studies come out that say red meat causes all manner of ill, I just wonder about the construct issues surrounding that. What kind of meat is it? I think that makes a difference. There's some new evidence I've seen as well that if you eat a lot of red meat, even good red meat that's been raised well, has been fed antibiotics, GMO feed, crap, etc., you still may get in trouble if you don't eat sufficient vegetables with it. So this is a moderation. So red meat may cause more health issues when you don't eat your vegetables with it. And by that we mean green leafy vegetables like organic kale, Swiss chard, all the things that most Americans don't like to eat, but have the proper nutrients that work with the high quality meats to produce, some would say, more optimal health. So these are the things that you think about as a scientist. A scientific mind doesn't take the conventional wisdom, the status quo, whatever the headlines are saying. A scientific mind thinks about the nuance and thinks about the construct validity, internal validity, etc. of these different questions. So that's the issue with construct confounding. Is it really red meat that causes the issues, or is it a certain kind of red meat? Is it a certain kind of red meat that's antibiotic filled, has had genetically modified feed that's been sprayed with Roundup and toxins? So, is it that red meat that's causing the problem, or is it all red meat, or what kind of things are we talking about here? I'm going to save these for program eval because I want to move on. If you really want to know, ask me in class, but I'm seeing I'm already almost at 30 minutes, so I want to keep going. Okay, so construct validity, an IO example here. So we have this Venn diagram. I love Venn diagrams where we have circles and they overlap. And so I just want to explain to you what it means to have good construct validity from a contamination and deficiency perspective. Okay, so this circle here represents, I'm sorry, let's go over to the circle first. Here on the right. This is our conceptual criterion of job performance. Let's say this is my job performance as a professor. And so this is the universe of possible behaviors that encompass my job performance. So it's all the things I do on a daily basis for my job. The things that you see and the things that you don't see as students. So that is called the ultimate or conceptual criterion or conceptual construct that we've talked about before. I think Fisk mentioned that as well in the readings. And then over here we have the operationalization of that construct, and we're going to use the one of supervisor ratings. Now I could have used you guys as student evals as well. That's another operationalization of my performance. To the extent that these overlap, we have construct validity or relevance. Okay, so my universe of possible behaviors, everything that I do for my job, and then supervisor ratings captures that to some extent, but not a lot. So let's think about the reason for why that might be. My supervisor, I have two actually, Dr. McKenna is my most immediate supervisor, and then we have the Dean of SPIFIC, who is another supervisor. Neither one of them really see a lot of my performance. They see me in administration meetings. They may look at my course evals to kind of see what I'm doing, but very rarely do they visit my classes. Very rarely do they see me interacting extensively with you, except maybe in hacking. So there's a lot of my performance that they don't see, and that is criterion deficiency, or the extent to which the operationalization does not cover the conceptual criterion or construct. Now, the criterion contamination aspect is all of the different things that the supervisor ratings are capturing that are not relevant to my performance. These are things like biases, maybe liking, maybe my supervisor, this isn't true in reality, but hypothetically, maybe he or she doesn't like me very much, and so that's going to maybe filter into the ratings. We know from research that attractiveness plays a role in how people rate each other. And that is contamination because it is not relevant to my performance. So you can probably think of other examples, but there are things in here that are not at all corresponding to my performance, but they're captured anyway. And so the goal is, how can we capture the criterion domain or the construct domain, conceptual criterion, in the most accurate way that we can, and give it the coverage that it should have. And this was why 360 ratings were invented, is because if we have supervisor, student, so students, you see more of my performance, probably a bigger chunk than this even, so you can rate it probably more effectively in some ways. And then maybe my faculty colleagues who come observe my class, so that way we get better coverage is the idea. Okay, so I'm sure you can think on your own of other examples and other contexts for this. Okay, let's move on to external validity. To what extent do the findings of my study extend across various things like settings and people, etc.? Now, I just wanted to say a quick word before moving on, because I think I explained it in the other slide, but I wanted to mention that people a lot of times will give throwaway lines. What I mean by throwaway lines are lines that in maybe the limitations part of journal articles or in presentations, well, they'll say, well, our findings our study was conducted on people in the United States, and therefore the findings probably won't extend to people in other countries. And then they move on. That is a throwaway line and is a blind critique, and it drives me crazy a little bit. Typically, I will always ask the question to those people, can you give me a theory as to why these results won't extend? Because to me, it seems like common sense to think that, results will probably extend unless I have a theory specifying why they would not. So my goal is to always provide a theoretical rationale. If I believe the results will not extend, then I should be able to provide a theoretical rationale for why they will not extend. And if I don't have a theory, then why even say it? So that's just one of my pet peeves with external validity. And coming up with a theory helps you think through, critically as a scientist. It's good practice at the very least. Okay, we're going to go through the potpourri of topics here. Categorical versus continuous variables. Just in case this is a new concept to you, I just want to quickly review it. Okay, so first, categorical variables. These can be also called discrete, or they can be called factors. You will see these words used interchangeably in the literature. Have you noticed that in the field of psychology there are 5 or 6 terms for the same thing? And I feel it is incumbent upon me to tell you all of the different ways we can say the same thing, because at conferences, people will use these things interchangeably, and so it's good to know. Just like for the IV, there are several ways to say the IV in our field. There's, of course, independent variable, predictor, what else? Antecedent, sometimes you hear. Sometimes it's the intervention. So there are several different synonyms that I put on the internal validity slide that I forgot to say, but you get the picture. Okay, so categorical variables are things like gender, what org you belong to, experimental condition. Were you in the condition where your mood was manipulated or your self-efficacy was manipulated somehow, or were you in the control condition where it was not? Continuous variables indicate a person's standing, usually on a latent construct of interest. A latent construct means an underlying abstract concept like cognitive ability, personality, etc. It also could be something more concrete, like your time that you've been with the organization, your tenure, how many years have you been employed here, the seconds it took for you to respond to a certain task. Those are all continuous variables that can take on a broad range of values. So sometimes it will be a scale from 1 to 10 when you're rating yourself personality 1 to 5. So those are continuous measures. And that's going to be important because the nature of the variable, whether it's categorical or continuous, is going to determine the type of stat analysis that you'll need to run. And in program eval, that's going to be much more important. I briefly wanted to introduce to you the difference between and within subject designs. And again, some of this may be completely review for you. If so, just skim on by. I want to talk with you about an independent t-test and what that looks like. So first, note on notation. This is SCC notation, Shatters, Cook, and Campbell, the book that you'll have for program eval. And the O's mean observations or measures of something, like you're taking a personality measure, a skills measure. And the X is the intervention or the IV, the thing that you manipulate in your experiment. The NR means non-random assignment. So that means that you're not employing random assignment. You're just doing a voluntary, people can self-select into your group. Or you have a situation like this scenario where you have employees in Department A attend a training class at one point in time, and everyone in Department B attends the same training class but at a different time. So you cannot randomly assign people to groups, basically. Then you take, you take a measure of their skills. And if the training is effective, we would expect to see a difference in means between Group 1 and Group 2. And we're going to use an independent t-test because there are different people in Department A than in B. So that means we'll do an independent t. Conversely, if we have a within subjects design, we have basically a pre-test and a post-test, and the same people in that group. So NR is kind of a moot point, so I'm just going to delete it so we don't get confused because we don't have two groups. So we're just going to test people at time 1 on some kind of skill and then give them the training and then test them again at time 2. Same people. And this is where testing effects can come into play. That is noted. If our training is effective, we expect a jump or a decline if we expect the outcome to decrease, like stress, between time 1 and time 2 for these individuals. And we are going to employ a dependent or paired samples t-test in this case. Oops. Okay, moving along. Now we have a mixed design situation where we do have two groups like the independent t-test, but we have a within subjects factor, and that is a pre-test and a post-test. So this gives us the benefits of both within and between subjects design because it is mixed, and we have a benefit in the sense that we can rule out a lot of threats to validity with this design. We can rule out the testing threat because if people are primed in this group, they'll also probably be primed in this group. And if this Group 1 or Department A still shows a significant jump between 1 and 2, more so than Department B, then we know, or we can at least have a little bit more evidence to infer that our training program or or our IV, whatever it is, has been effective in moving the dial on the DV. So the stat analysis for a mixed ANOVA is for this particular design is a mixed ANOVA, and it's fairly simple to run in SPSS, and it tells us basically, was there a difference between Department A and B? So again, was this jump higher than this jump here in Department B? Okay, to wrap up, I just wanted to provide a few pointers for how to process a scientific study when you're reading it for this class and future classes. First, take note about how the author builds a case with theory. So in the introduction, typically authors will use compelling logic and theory to make a case for why they expect certain results to happen in their data. Especially for doctoral students, note the theories mentioned and file them for later reference when you're studying for comps. Hopefully, my goal for you is that the names will start to look familiar over time. And it may not be at that stage quite yet, but soon you'll start to see overlap. You'll start to see social identity theory, for example, Tajfel popping up more. You'll start to see theory of planned behavior more, and other maybe stereotype threat and other things. Those pop up over and over again across studies. Identify the IV or the causal variable and the DV. So whatever those are in the particular study. This is just an example in an IO context. Note how each variable is operationalized. So is the operationalization appropriate for how the authors have defined the variable? And I'm surprised sometimes that those two aren't always linked as much as I would have thought. Sometimes the authors put a name to a variable that's very different from how they actually measured or captured it or manipulated it. So that's always interesting to me. Which threats to validity could be operating? So think about confounds, threats to internal validity, and stat conclusion validities as well. What information is still missing? So if you could ask the authors a question, what would that question be? That's something that helps me to organize my thoughts and helps me to think about future research questions as well. Now, in the notes below this particular slide, I provide some YouTube links to some fascinating studies that I have wanted to show in class, and if we have time, I will, but please on your own, watch some of these. This is one where they had a Confederate stealing a bike in a park, and the Confederate was either white male, young male, African-American young male, and then a young female. And you know what, I'm going to have to show that in class at some point. It's just hilarious. But it's a good exercise for practicing identifying the IV and the DV and how they're operationalized. Are there any alternative explanations for what happened besides what the people concluded in the clip? Solomon Ash's study on conformity with the line length is very interesting as well. So these are just 2 or 3 minute clips, I believe. This one may be a little longer. And then the bridge study, this is fascinating. So this is about physiological arousal and sexual attraction. So we'll talk more about that in class, I think. And so it's just good practice for identifying what is the IV, what is the DV, and how were they operationalized, thinking about different causal explanations, and finally, what do the results say about human nature, and what are applications for the workplace from all of these different studies? So those are some questions to ask as you think things through. Well, thank you, and I look forward to seeing you in class, and continued best wishes on this journey where you are learning this new scientific language and ways of thinking.